Hello world, it's Rahul. Welcome back guys to machine learning tutorial. So we have seen how mathematically we can derive equation for hyperplane and margin. Now we have a margin function with us. So here we have to minimize that by using quadratic optimizer as we have discussed in last video. So guys, if you haven't watched that, first let's have a look into that so that you have clear understanding of what we are going to discuss over here. I have attached the video links into the description. Let's have a quick recap what we have discussed in last video. So we have find hyperplane equation, that is W transpose X plus B is equal to 0. Then positive and negative margin line equation and total marginal distance, that is 2 over norm of W, which we have flipped so that we can maximize the margin by minimizing the W term. So now we have to minimize the objective function, that is square of norm of W over 2. So guys, I have already told you in last video that here we will be going to use quadratic optimizer as our objective function is no more linear in nature, and here we have some constraints as well with us. So for understanding this, let's first see how we can solve this optimization function with constraints. Now let's say we have an equation of f of xy is equal to x square minus 3y square minus 4. So here we want to minimize this function with respect to term x and y. So guys, we can solve this by computing the gradient into this equation, as we have solved so many problems earlier by taking derivatives of function. So for x square, derivative will be 2x. For minus 3y square, derivative will be minus 6y. And derivative for constant will be 0. But what if I add some constraints over here? Let's say g of x and y is equal to x minus y minus 2 is equal to 0. Now if I directly optimize my objective function through gradient descent, then there will be chances of not satisfying the constraints. So guys, if you can see on the screen, we have an objective function drawn on the graph and we want to optimize this. Now we know that our function will be optimized at minima point, so we can compute that if we don't have any constraints for as of now. Now suppose if I provide some constraints like x can only be less than this or greater than this. So now if you can see, our earlier solution will not be correct, because now we have to find out maximum in both the region. So that is why we are using quadratic optimizer over here instead of gradient descent. So now we can conclude why we are not using gradient descent over here. First, our objective function is not linear in nature. And second, we have constraints with our objective functions which cannot be handled by gradient descent technique. So guys, now let's see how we can optimize our objective function, that is square of norm of W over 2. And let's say we have two constraints with us as shown on the screen. So what we have to do now is we have to combine our objective function and all provided constraints so that we can compute optimization function on that. But here question is, how can we add constraints with objective function? So guys, we will multiply each constraint with alpha and add them with objective function, so that we have to optimize the function with respect to term w, b and alpha for getting the results. Now we have new objective function, that is half of square of norm minus alpha 1 times function g1 minus alpha 2 times function g2, and this will be subject to alpha 1 and alpha 2 greater than 0. Guys, one thing to note here is, if constraint is greater than 0, then we will put negative sign before that, otherwise we will assume it as positive. And here we are using alpha term for inequality constraints, whereas we will use beta for equality constraints. So now we have formulated the new objective function with constraints as mentioned. Now let's say we have n number of constraints with us. So we will rewrite our objective function as shown on the screen, where we have our original objective function and then we will add all of these constraints using the Lagrange multiplier. So this is the final objective function. Now question is how to solve this. So guys, here I have defined the function as theta of p, which is function of only w term as shown on the screen, and it is the maximum value that our L can take for any alpha and beta. So we already know that we have to minimize the term w for getting the optimal solution, and if I minimize the theta of p, which is nothing but the function of w, we will get our optimized solution. So if I write the above equation as p star is equal to min of theta of p is equal to min of w times max of L of w alpha and beta, such that alpha beta and all of alpha I should be greater than 0. Now let's say we have generalized objective function as shown on the screen. So guys, one thing to note here is we don't have any beta term, as in support vector machine we only deal with inequality constraints. So according to primal Lagrange, first we have to maximize the alpha and beta terms, that is nothing but finding the derivative of function with respect to alpha and beta, and then we will minimize the w term in equation, that is deriving the function with respect to w. Now whatever w we will get, suppose our g of I is negative, so for maximizing this term, what we will do is we will make it very large negative infinity, so that negative negative will become positive infinity, and then we will minimize the w term in the function. So guys, this is all about primal Lagrange multiplier for finding the optimal solution of these type of objective functions. Now let's say if I switch the order, and when I say switch the order, that means if I first minimize the function with respect to some coefficient and then do maximization of that function, then it will be known as dual optimization technique. So guys, in dual formulation, what we do is we first do minimization over all w term, and then we do maximization over all alpha and beta terms. So in primal optimization, what we were doing is first we were maximizing the function and then minimizing that, which is opposite to this. So guys, just to add one thing, that d star will not always be equal to p star. In some cases it may be, but for most of the time d star will be smaller than p star, because max of min of a function is always less than or equal to min of max of a function. So guys, I have told you different mechanisms for finding the optimal solution for support vector machine. We can solve our problem from either primal optimization or dual optimization. Now, if we have clear understanding of primal and dual optimization technique, we can solve our generalized equation by first deriving that with respect to w, and we will get w plus sigma of alpha n into yn into xn. Same we will do with respect to beta and get sigma of alpha n into yn. Now we will feed these values into generalized equation to get the dual optimized function as shown on the screen. So guys, if you can see, we can directly eliminate last term, that is sigma of alpha n into yn into beta, as we got derivative of this term as 0, what we have seen just now. And once you will put value of w transpose x in second last term, it will also get eliminated. So we will have first two terms with us as shown on the screen. So this is how dual formulation looks like. So first term is what we have seen just now, and last term we are getting by multiply the w transpose term with w term. So this is the new optimization function which we have to optimize. Now we don't have w term in this equation, so we have to maximize this function, and once we get the value of alpha, we will substitute the alpha value in this equation and get the w value. And if you can see the equation, we are multiplying the alpha term, that's why it's becoming dual quadratic optimization. Now let's understand why we did this dual formulation, why we just not stick to primal optimization. So you can see on the screen, we have solved the dual function where each x is occurring as an inner product which we can replace with some other kernel and use it to learn support vector for nonlinear data. While predicting as well, we are getting inner product of x as we have an equation of y is equal to sine of w transpose x plus p, what we have seen earlier. And if I substitute the w value over here, then we will be computing inner product of all the training data points and x. Now we can fit any of the kernel over here and use it for nonlinear data as well. So guys, this is all about formulation of objective function and solving that with the help of quadratic optimization of primal and dual Lagrangian. Thank you guys for your time. Do like, share and subscribe. Hit the bell icon to get the latest updates. Happy learning and stay safe.